So we ended here last time. Remember, when we're looking for eigenvalues, we're looking for solutions to this non-trivial solutions to this system of linear equations, right? We're trying to replace matrix multiplication with scalar multiplication. We turned that into a homogeneous system, right? Subtracted over, wrote lambda x is lambda times I times x, and factored out the x. Again, we want non-trivial solutions. So we want this matrix that's multiplied by the x to be not invertible. Our check for if something is not invertible is with the determinant is checking to see if the determinant is equal to 0. So this gives us an equation to solve for lambda when we're done. We refer to this as the characteristic equation. The left-hand side is a polynomial in lambda, so we refer to that as the characteristic polynomial. So this was the example we were working on at the end of class last time. Pardon me. I talked a little bit about what the polynomial would look like when we're doing the determinant. We already know what the answers are because we did that at the first example last time. We can factor out a 1 minus lambda out of both terms. We just want to see that what we get out of this. Declan, before you get too far. There you go. Yep. I can factor out 1 minus lambda out of both terms. Because again, I'm trying to find the 0, so I want to factor it, right? So I might as well factor out a 1 minus lambda. So I certainly see that if I set this equal to 0, we'll get one of the answers is 1, right? One of the roots is 1. If you multiply out what's on the inside, we get lambda squared minus 5 lambda plus a 4, and then plus a 2 on the end there, right? Adding the 4 and the 2 together gives me a plus 6, and then I see that that factors as lambda minus 2 times lambda minus 3. This is literally the example that we had at the beginning of class last time. Not the beginning of class, the end of class last time. And we already saw that 1, 2, and 3 were the eigenvalues. We wouldn't have known that ahead of time, except I gave you eigenvectors, right? And we were able to deduce what the eigenvalues were from the eigenvectors. If you're given a matrix, this is what you would need to do to figure out its eigenvalues, right? And now I see the eigenvalues are 1, 2, and 3. So again, if we set this equal to 0, then I get my lambdas 1, 2, and 3. How do we find the eigenvectors that are associated with each of these? Well, remember again, these are the values that give us non-trivial solutions to this equation, right? Or not this equation. Or you erased the wrong one. This one, or underline the wrong one. That equation, right? So if we want to figure out what the eigenvectors are associated with each of those, then I'm going to go back to my original matrix. I'm going to subtract off those values off the diagonal, row reduce, and write down the solutions to the homogeneous system. Okay. So let's start with 1 first. Again, these are the values that we're going to subtract off the diagonal. So when lambda is equal to 1, I'm going to start with the matrix 3, 0, 1, negative 2, 0, 0, negative 2, 0, 0. Because I'm subtracting 1 off the diagonal, right? So just subtracting 1 off the diagonal entries. Everything else stays the same. Yeah. Okay. If we row reduce, you should get 1, 0, 0, 0, 0, 1, 0, 0, 0. Certainly I can make this a 1, 0, 0 and move it to the top. That would cancel off that. When I cancel off the 3, I'm left with that 1, right? Where's the free variable? Column 2, right? You always will get at least one free variable if you're doing these problems right. We're looking for non-trivial solutions, right? If you row reduce and you get the identity matrix, you've done something wrong. Okay? We always have to get non-trivial solutions. So if you row reduce and get the identity matrix, something went wrong somewhere. You need to go back and check where the error is. This is lambda equals 1. Yep. So here, our free variables here, the other variables are 0, right? So you would have x is t times 0, 1, 0. And if we go back up, here, isn't 0, 1, 0 one of the vectors I gave you last time? All right. So here we would have t is the parameter, 0, 1, 0 generates all of the solutions to that particular equation, right? So we would say that the vector 0, 1, 0 forms a basis for we refer to this as the eigenspace associated with lambda equals 1. No, lambda 0, 1, 0 is only the basis for lambda equals 1. You still have to do lambda equals 2 and lambda is equal to 3. Yep, you have to do all of them. Each eigenvalue will have a different eigenspace associated with it. So we would also need to do lambda equals 2 and lambda is equal to 3. Let me show you a little bit of a shortcut that you can do on your calculator so you're not having to type them all in by hand every single time. So our original matrix here was, clear, second matrix, edit, that's what I want. Our original matrix is 4, chords in the way, sorry. The original matrix is 4, 0, 1. What did I do over here? 4, 0, 1, negative 2, 1, 0, and negative 2, 0, 1. Okay. That's the original matrix that we have. Or not. Apparently that doesn't work for Zoom. Try this one. Better? Okay. All right. So I want to row reduce. So using our REF like we have in the past, I want to go back and grab my matrix, but I need to subtract the eigenvalue off the diagonal. We can do that by doing minus, I'll do the one for 2 here. I want to do 2 times. If I go back over into the math menu, there's an identity matrix function. In this case, I want the 3 by 3 identity because A is 3 by 3, right? So what that will do at this point, we'll take the identity matrix and multiply it by 2. So it puts 2's down the diagonal, right? This effect is just subtracting 2 off the diagonal. Right? I can row reduce that. All right. So for lambda equals 2, the reduced row echelon form is 1, 0.5, 0, 1, negative 1, 0, 0, 0. And I know you can't see what I'm writing on the board right this second, but I also want to make sure you have a chance to type that in if you want to. And we're going to come back over to this in a second as well. So go back over to here. There's our reduced row echelon form. What are the solutions then? We have a negative a half, a 1, and a 1 here, right? And that would be anything times that, right? So your basis would be, this would serve as a basis, or any multiple of it would serve as a basis, right? So if I multiplied, say, by negative 2, that would work as a basis, because I can do any constant multiple. And again, if you go back to the example we did at the end of class last time, pretty sure that was what I used for the eigenvector in that one, didn't I? If I scroll back up. Oh, look at that. Well, I guess it was a negative, right? It was a negative 1, so I multiplied by a 2 instead. All right. So the last one here, now that we've got this thing already typed in, I can do this pretty easily to change it, because all I need to do is change the 2 to a 3 to get the next one, isn't it? I don't have to retype everything. If you use second entry, bring up the old entry, or go up and just arrow up and grab it. I just need to change the 2 to a 3. Matrix, under the matrix menu, go under math. Matrix, math, and it's number 5. I'm taking the eigenvalue and multiplying it by the identity. So I put the eigenvalue down the diagonal, so I subtract it off the diagonal. Okay. Basically, I'm just doing this, right? That's what's inside there. And I'm doing a minus lambda I. And here the solutions would be, your basis would be what? Negative 1, 1, 1. Which again is what we use for the other eigenvector. And again, any multiple of it is also an eigenvector. It generates all the eigenvectors associated with that. Let's do the next one. First thing we want to do is we want to take the determinant of the matrix and subtract off lambda down the diagonal, right? We'll take the determinant of that matrix. This is a 2 by 2, so that's pretty straightforward, isn't it? We agree? It's pretty straightforward. I would have negative 2 minus lambda, 1 minus lambda, and then minus a 4. If we multiply everything out here, we'll get a lambda squared. I've got plus 2 lambda minus 1 lambda, so I'd have a plus lambda minus 2, and then minus 4 is still on the end. So you get lambda squared plus lambda minus 6. Notice that, one thing to notice, one of the properties here. Again, we refer to this as the characteristic polynomial. The constant term on your characteristic polynomial, that is the determinant of the matrix. Why? Why is that the determinant of the matrix? If I put 0 in for lambda, that gives me the constant term, doesn't it? If I put 0 in for lambda, I get the original matrix. So the constant term is always the determinant of your matrix. Okay? It's also true that the coefficient on your lambda is the sum of the roots of a polynomial. You always get the sum of the roots.
You said the constant term is the determinant. What? Did you repeat that?
Yeah, the constant term is always the determinant of the original matrix. Because I would put 0 in for lambda, it gives me the constant term. If I put 0 in for lambda, it gives me the original matrix. So the constant term is always the determinant of the matrix. That's your characteristic polynomial. To find the characteristic equation, we set that equal to 0. That's the only difference between characteristic polynomial and characteristic equation is that you set the polynomial equal to 0. Okay. We can factor think I lied when I said there was a sum of the roots. But anyway, doesn't matter at this point. Okay. We had lambda equals -3 and lambda is equal to 2. Right? Okay. So again, we can find our eigenvectors associated with each of these by putting the eigenvalues into this matrix here and row reducing, right? So let's go back over to the calculator so we can do it a little bit more quickly. I mean, I could row reduce it by hand, but I want you to use the technology. So let's change, this over to B. B is already a 2 by 2. Do -2, 4, 1, and 1. That's the matrix B. Our two different eigenvalues in this case were -3 and +2. I want to subtract off -3, right? So I'm going to do matrix plus 3 times the identity, because it's minus a -3 in this case. Also, make sure you change your identity matrix now to a 2 by 2, since the matrix is a 2 by 2 to start with. Okay. Yes. I'm sorry? On the calculator, it's under math and number 5. Okay. All right, so that's the matrix we get. So I'll go back over and write it down here. So the matrix we started with would have been +1, 4, 1, +4, right? Subtracting -3 off the diagonal. We row reduce. We got, I mean, this one would have been pretty easy to do by hand, but that's what we get, isn't it? Okay. So your basis for your eigenspace now is what? Yeah, -4, 1. Good. That's not new, right? This is basically the basis for your null space for the matrix we just created, isn't it? Okay. Not new at all. Yes, Kevin. Remember, I'm solving the homogeneous system, right? Pretend like there's zeros there. Yeah, we're finding the null space of the matrix. We're just solving the homogeneous system. So this would be T. So this column would be T. That would be a -4T, right? So pull it off the T. Okay. Do the same thing for +2 now. Let me go back over to the calculator. Change this to -2. Okay. And get 1 minus 1 there. And I can go back over to the original and see that okay, 2 by 2s aren't bad. You could do them by hand pretty quickly, but might as well use the technology. Okay. We're going to use it a lot here in a second. All right, so for lambda equals 2, the matrix that we started with would have been -4, 4, and 1, -1. And that reduces to 1, -1, 0, 0. So your basis for your eigenspace in this case is what? 1, 1. Good. Good. Questions?
What you put in your calculator for that? Oh, you go -2.
Yeah. Yeah, we always subtract the eigenvalue off. The reason why it was a plus in the previous one is because we're doing minus a -3. Because the eigenvalue was a -3. Yeah. Say that again? The reduced row echelon form of what?
The matrix.
Well, yeah, if you do the reduced row echelon form of the matrix, you're going to get the identity matrix in this case. I know I'll get the if I just put the original matrix in and do the reduced row echelon form, I know I'm going to get the identity matrix because I said this is your determinant. So if that's the determinant, it's not 0, so the matrix is invertible, so it'll row reduce down to the identity. So yeah, don't do that. You don't want to get the identity matrix when you're done. You want to get something that has non-trivial solutions. Again, anytime that you do your row reduction, you better get at least one row of zeros. We want non-trivial solutions. If you don't get any free variables, you've done something wrong somewhere along the way. Yeah.
So do you make it like you add a negative to the end for the basis for I space? Like what? How do you like that?
Okay, so remember again, we're trying to find the null space of this matrix, right? So your x2 would be t, your x1 would be a negative 4t because I have to subtract it to the other side, right? Because remember again, we think about having that zeros being augmented there. And then I'm just factoring off the t. That's why it's negative. Your signs are going to switch when you move it to the other side of the equation. All right. So let's think about some other properties here. What happens if your matrix is triangular? So for example, if I just had the matrix say 1, 3, negative 2, 0, 5, 1, 0, 0, negative 7. What are your eigenvalues? Shouldn't have to do any work at all. How do we find eigenvalues again? What do we do first? Of a minus lambda I, right? So your first step is to subtract lambda off the diagonal, correct? Step 1 is subtract lambda off the diagonal. Step 2 is take a determinant. How do you take the determinant of the triangular matrix? Yeah, let's multiply the diagonal entries, right? So your characteristic polynomial here will be 1 minus lambda times 5 minus lambda times negative 7 minus lambda. It's already factored, right? So what are your eigenvalues going to be? It's just 1, 5, negative 7. It's literally just the entries, right? Because you'll have 1 minus lambda, so lambda would be 1. You'd have 5 minus lambda, so it should be 5, right? So for a triangular matrix, the eigenvalues are the diagonal entries. Eigenvalues are very, very easy to compute once you do, or if it's in triangular form. Right? Okay. How about looking at your eigenvalues in terms of invertibility? Well, I told you there's a couple of ways to think about it. I told you a minute ago that the constant term here is your determinant. If it's not going to be invertible, what does your constant term need to be? 0, right? If your constant term's 0, then what are you guaranteed is going to be an eigenvalue no matter what? If the constant term is 0, what can you factor out of every term in your polynomial? Lambda. So what root would that correspond to if you factored out a lambda? 0, right? So if 0 is an eigenvalue, then you know your matrix is not invertible. Okay? So it's invertible if and only if all eigenvalues are non-zero. If you have all eigenvalues are non-zero, then you have an invertible matrix. Think about it again. Remember again, this is the system that we're trying to solve, right? Yeah. If this thing is invertible, then we would have, pardon me, If this thing is invertible, then we'd only have the trivial solution, right? Agreed? So if lambda equals 0 as an eigenvalue, I would not want A to be invertible to have this have non-trivial solutions. Okay. So if it's invertible, then all of these would need to be non-zero. Make sure that I actually have to subtract something off to make it not invertible. All right. What happens with when we do powers here? This is interesting. At least I think it's interesting. And this is the whole point, by the way. Well, one of the points. Say we have an eigenvalue and an eigenvector. That means we have this equation, right? Well, say I want to do a squared times b. Well, a squared is the same thing as a times a, right? Agreed? What can I replace the a times v with? Lambda v. And then I can move the lambda to the front, right? And what can I replace a times v with? Lambda v again, right? So I get, at the end here, just to summarize, we've got a squared v equals lambda squared v. So if lambda is an eigenvalue for a, what's an eigenvalue for a squared? Lambda squared, right? Could I do it for cubed? Yeah. Could I do it for the fourth power? Yeah. Right? Could do it forever, right? So lambda to the k is an eigenvalue for a to the k. Notice the eigenvector doesn't change with associated eigenvector phi. This is one of the reasons why we care about eigenvalues. The whole point of this is to replace matrix multiplication with scalar multiplication when I can. What's easier to do powers of, matrices or scalars? Scalars, right? There are applications in what's referred to as dynamical systems where you want to do repeated matrix multiplication. If you have done Markov chains before, I know some of you have done some Markov work in computer science, for example, right? If you do Markov chains, one of the things that you want to do is analyze what happens in the long term. Well, Markov chains is multiplying by a matrix over and over and over and over again. Well, to be able to do a long-term analysis, it's much easier to replace that matrix with a scalar if you can and analyze what happens with that scalar. That's just a limit. Then you can start doing things with calculus on these things, with limits. Okay? This is one of the reasons why. All right? This formula also works, by the way, for negative exponents if your matrix is invertible. Okay? It works for any matrix if it's non-invertible or invertible, but if it's invertible, you know your lambda is non-zero, so I can divide by it. So it also works for invertible matrices as well. Okay. But again, this is one of the big points about eigenvalues and eigenvectors. I can replace matrix multiplication with scalar multiplication, which means that I can do long-term analysis of what's going on in a system where it requires me to do matrix multiplication by replacing the matrices with scalars when I can. This is the point. Okay. All right. Let's do another example. This one looks kind of ugly, right? So let me show you how you would attack this with technology to find the eigenvalues. Okay. In particular, let me show you how you would do this on your calculator. All right. So the matrix in this case is a 4x4. We had 3, 1, -4, 0, -18, -8, 24, 0, negative 4, negative 2, 6, 0, 15, 8, negative 20, negative 1. Okay. What's that? Well, I'm doing it one-handed out up here. I can do it even faster when it's in my hands. Okay. All right. So that's typing in the 4x4 matrix here. That does not look like something I would necessarily want to do a determinant by hand, does it? Because think about what you would need to do. First, I would need to subtract lambda off the diagonal. Then I have to do the determinant. Then I need to multiply everything out and refactor it. That sounds like it sucks a lot, doesn't it? Okay. Now, computer algebra systems, many of the computer algebra systems have things that you can type in a matrix and it'll tell you the eigenvalues and the eigenvectors immediately. Of course, you're not going to have that on the final, so let me show you how you can kind of backdoor it with the calculator. All right. So here's what we're going to do. I'm going to go into our graphing menu. Okay. And up here, I'm going to just type in the determinant of a minus lambda I, except I'm going to use an x where there's a lambda, and I'll use that identity function for the I. Okay. So go into matrix, math, determinant, matrix A, minus, I'm going to use x for the variable, and then multiply by the 4x4 identity. Okay. That's what the syntax looks like it there. What do we want to know about this? We want to know when it's equal to 0, right? Okay. So we're going to use the graphing capabilities on your calculator and figure out where it crosses the x-axis. Calculator will do that. So let's just hit graph. Might take it a minute because it has to compute the determinants. It doesn't take too long. Yeah? How to do what?
Yeah, I only got like one side.
Let's see what you typed in. That's because you need to change your window. Yeah, you're over your lowest side, and then go back over and change your low x value. Yeah, you got your x value set at 0. Yeah. All right. So now you can use the root functions in your calculator to be able to get those zeros. Okay. So go to second calculate, which is above your F4 right here. It asks for the second one is to find a 0. Okay. And then if you haven't used it before, you just move your cursor to the left of where you think there's a 0. You move your cursor to the right of where you think there's a 0. And then you guess where it is and hit enter, and it'll find it. So one of them's at -2, which you might have been able to guess by looking at the scale, right? Yes.
How do you use the cursor to guess where it's 0?
Say that again.
How do you use the cursor to guess where it's 0?
Well, I'm just using the left and right buttons. These, the arrows.
How do you know where it is?
Second calculate. So that's to the left, right? That's now to the right. And then I just move it to where I guess it is, and then just hit enter, and it goes to the next one. Just do zoom standard. Do zoom standard. And that'll get you back to a 10 by 10. I would start there. You can probably guess what the other two are. 1 and 2. Okay. All right. So get out of this. Now I can just start putting them in. We said one of them was -2, it looked like. Do we agree now that one of them is -2? Yep. Yep, because I got that row of zeros, right? Do I agree that -1 is one of them? Yep. Do we agree that 1 is one of them? Yeah. And then finally, 2. This is not only verifying that we really did get an eigenvalue, but it also helps us find the basis, doesn't it? All right, so again, there was our first one, right? Okay. -2 is the first one. And if I wanted to, oops, I didn't grab the right one. You could also do, make them fractions, so you can see them as fractions, right? So again, we've got that free variable on the right, the x4. So in that one, you would have a basis of, well, the x1 is 0 for certain. The x2 is -1/3 times the fourth one. That was -12, so I could multiply everything by 12 if I wanted to get rid of the fractions. So if I flip back over here real quick, okay, so that's not what I wanted to do. For lambda equals -2, our reduced row echelon form is 1 0 0 0 0 1 0 1/3 0 0 1 1/12 0 0 0 0. And then your basis for your eigenspace would be, well, the first entry is a 0. The next one I could use a -4. The next one I could use a -1. And the last one I could use a 12 if I want to get rid of the fractions. Multiply everything by 12. That okay? And then you would do the same thing for the other ones. Okay. Now that you have the function, if you've typed it into your calculator, now that you have it typed in, you can just edit the function and just leave it in there. Right? You don't have to retype it every single time. If you've got it in your calculator already, you just leave it, right? And just change what you need, depending on the size, right? If it's a 5 by 5, you change that to a 5. If it's a 3 by 3, you change it to a 3, right? Also, if you already have that typed in there, notice that there's under your VARs, oh, you can't see where I'm pointing because it's off the screen. Under the VARs menu here, right there, you can get to your Y variables this way. So notice it's got your list of the Y variables in there. That, if you type your function in the Y equals menu, you can actually use that without having to retype it in each time. So let me show you what I mean. So we said that we've already got typed in this determinant in here. And we said that 2 was an eigenvalue, right? So instead of retyping everything, if I do row reduce, I could do row reduce y1 of 2. That'll put 2 in the x and do, whoa, oh, it didn't work. Oh, it's because it's a determinant. Sorry, I apologize. I can't do it that way because it has the determinant in it. Sorry. But if I can do the just y1 of 2. I lied. If I can do y1 of 2, I should get 0. I can actually plug that in. I'm sorry, I was trying to row reduce the determinant. It doesn't make any sense. If I didn't, I could do it the other way. If I take the determinant out and just have it like this, then I can do what I told you could do. And it'll do it that way. If I take the determinant part out, it'll do it that way. Might save you some typing. You don't have to do that if you don't want to. Okay. Just might save you some typing. It's a good thing to practice with. All right. Questions on the calculator at all? All right, let's make our last update to the mega theorem. We haven't seen this one for a while. Might want to go back and review it for the final, of course. All right. What letter are we on? Was it? What did you say? 76. You? All right. So I've got a couple of ones to put in for transformations because we didn't put it for linear transformations. Remember we used that T sub A notation to denote the transformation that's multiplication by A, right? So U is going to be T sub A is 1 to 1, which means V will be T sub A is on to, and then the last one is with terms of eigenvalues, all eigenvalues of A are non-zero. Yes.
When you say T is what? T is 1, 2.
Yep.
Like
Is that?
and you put it as one of the mega theorem.
Right. Remember that T sub A is our notation for multiplication by A.
So we put everything that's supposed to.
Say that again.
We put in everything that can happen to something.
Everything that we're saying is equivalent to the matrix being invertible. Yeah. All right. So, in the last few minutes we have left today, and we'll finish this up on Friday, we're going to talk about what's referred to as diagonalization. All right. So what do we mean when we're talking about diagonalizing a matrix? Well, if I talk about diagonalizing a matrix, I probably am talking about some sort of a diagonal matrix, right? Yeah, I hope. Okay. All right. So when we're talking about diagonalizing a matrix, we're looking for an invertible matrix. We typically refer to it as P, and a diagonal matrix D, such that if we do pardon me, goodness. If I do P inverse A P, I get D. Or I could write it the other way. I could say A is PD P inverse. Either way works. Okay. So A is diagonalizable if I can find this matrix P, so that when I multiply A by P inverse on the left and P on the right, I end up with a diagonal matrix when I'm done. Why might I care? This seems like something just kind of random to throw in, and why might I care? Again, we already talked about that. If we wanted to do higher powers of matrices, it would be nicer to be able to do scalar powers versus matrix powers. Computationally speaking, that's easier, right? What would happen if I wrote my A this way? Well, A squared would be PD P inverse PD P inverse. What happens in the middle? Yeah, the P inverse P cancels, doesn't it? And we just end up with P D squared P inverse. Could I do it for cubed? Yeah. Could I do it for fourth power? Yeah, right? So I can replace this matrix power with this one. Why is it easier to do this one? Well, if it's a diagonal matrix, how do you take powers of a diagonal matrix? If I asked you to do 5007 and told you to ask you to square it, what would you get? 250049. I just have to square the diagonal entries, right? That's a lot easier, isn't it? Computationally speaking. Okay. This is why we care about diagonalization. So let's look at this particular one real quick, and then we'll talk about how we find this next time. Let's see if I take, we can do P inverse. It is a 2 by 2, right? So remember how you do inverses of 2 by 2s? Do 1 over the determinant times, you flip the main diagonal, negate the off diagonal, right? Determinant here is 3 minus 4 is negative 1. So you'd have 1 over negative 1 times negative 1, 4, 1, negative 3. Right, remember you do 1 over the determinant and then times the adjoint. The adjoint for a 2 by 2 is flip the main diagonal and negate the off diagonal. Okay. So if I do 1, negative 4, negative 1, 3 times negative 11, 36, negative 3, 10 times that other matrix, rather than doing this all by hand, we do it this way. Oops. No, this would be quicker if I knew what I was doing. So A is negative 11, 36, negative 3, and 10. And if I edit my B, which is negative 3, negative 4, negative 1, negative 1, I know I'm out of time. If I do B inverse A, B, when you do this, you should get 1, 0, 0, negative 2 when I'm done. Yes. I just put it in the calculator, yeah, rather than doing this, rather than doing it by hand. So I got 1, 0, 0, 2. So this is my diagonal entry, right? Okay. All right. So what we're going to be interested in next time is how do we find this diagonal matrix, and then how can we find this matrix P if we can. We can't always do it. We'll talk a little bit about when we can do it. You might guess what these values are here. What do you think these values are here relative to the original matrix? Considering the chapter we're talking about, what do you think those values are going to be? They're going to be the eigenvalues of the matrix, yes. Okay. All right. So we'll do that next time. Yeah.
So are we doing the equation of P, the inverse P times A times P, or is it P times B squared times P?
I was just doing this one here.
Okay.
Yeah. Yep. Just to show that it was diagonalizable. Yeah. All right. Have a good one. We'll see you on Friday. Yep.
When do we get to use the P squared P inverse?
Say it again.
When do we get to use the P squared P inverse?
If you're trying to do higher and higher powers of the matrix, that's when you're going to use it.
So if it's a D power 4, the D has to be power 4.
Yeah. Yep. Whatever the power is here is going to be whatever the power is here. Yep. Assuming you can do it. You cannot always diagonalize matrices. Not all matrices are diagonalizable. We're going to talk about that next time. We will talk about when that's possible. It turns out it has to do with the number of eigenvectors that you can find. Number of linearly independent eigenvectors you can find, I should say.
I will be here Friday.
Oh, okay.
I found out yesterday we're going to meet on Saturday now instead of
Oh,
Friday.
okay, cool.
I actually told him I couldn't miss linear algebra.
Oh,
and they
yeah.
said, okay, we'll change.
We'll
where
change what we're
going.
gonna. Oh,
Yeah.
gotcha. Okay,
So.
sounds good. All right, we'll see you Friday then.
Yeah.